Good afternoon. Welcome to the ENTRUST Solutions webinar series on May 25th, 2003. Today's subject is rotor vibration fundamentals. My name is David Butts, and I'm a senior consulting engineer with TGA, which is part of the ENTRUST Solutions Group. ENTRUST Solutions Group. ENTRUST Solution Group is a ENR top 100 company that provides comprehensive and dependable engineering, consulting, and automation services to pipeline companies, gas and electric utilities, and industrial companies. They've been around for 20 years, and they have around 3,000 employees all over the US. I work for TG Advisors, which is within ENTRUST Solutions Group. We are a network of experts with extensive OEM, utility, and engineering consulting experience who have designed units operating worldwide. We were founded in 1991. We were incorporated in 2004, and we joined ENTRUST Solutions Group in April of 2022, so just over 1 year ago. We have two main offices. We have an office in Wilmington, Delaware, and we have a new office down in Greenville, South Carolina. This slide goes over some of our TGA service highlights. Because we are a network of ex-OEM engineers, we have a variety of services. We have steam and gas turbine generator health assessments, outage cycle optimization. It's a very long list, and it covers all the expertise all of our individuals bring to the company. Some background on myself. My name is David Butts. I am a senior consulting engineer with TG Advisors. I joined about 6 months ago. Prior to TGA, I worked with General Electric. I was with GE Power for 18 years in primarily gas turbine design roles within the turbine rotor. My last role with the company before I left was HA rotor technical leader. I have an educational background in mechanical engineering and material science and engineering. Our webinar outline, we will discuss the vibrations. We'll go through some simple case studies and then pause for questions. Mass eccentricity and vibration. How does it happen? Unbalance will occur when the mass of a rotating structure is not evenly distributed around the rotational axis. This unbalance results in vibration during operation. How is this fixed? Typically, the fix is an addition or removal of mass to better align the rotational axis with the mass axis. There are some examples around us every day. The tires or wheels on our car have little weights that are added. This is an example of mass on balance correction. Not many know, but there are mass on balance corrections for ceiling fans. So if your ceiling fan is vibrating during the high speed setting, you can actually add weights to correct that. The far right picture on this slide shows a mass off balance correction for a gas turbine compressor wheel. In the power gen world, vibration can result in unit inoperability or catastrophic failure. Balancing is the process of reducing the amount of vibration to acceptable levels. The force of an eccentric mass can have an impact on the vibration of the rotating structure. The picture in the upper left of this slide shows someone spinning around in a circle holding onto a mass attached to a string. As this person spins faster and faster, the felt pull is a function of its speed. So the pull force is equal to the mass times the radius, which is the length of the string, and then how fast they're rotating squared. So the pull force is a function of weight, radial location, and speed. Long gas turbine blades can have pull values of over 1 million pounds per blade. Because the pull force is a function of weight, radial location and speed, a small mass at a very large radius can have more impact than a large mass at a small radius. The graph in the upper right-hand corner shows the pull force for a string that's 18 inches long. The blue line is a weight that is 60 grams, and the orange line is a baseball. And at 3,600 RPM, something that is 60 grams will feel like 1,000 pounds. A baseball would feel like 2,000 pounds. Here are three sources of eccentricity in a rotating structure. Non-symmetric mass is the most simple example. An example of this is the center of mass not being aligned with the axis of rotation. This can happen with variation in your turbine or compressor blades. Another example is simply that the shaft is not straight. A bent shaft due to assembly or manufacturing or an event during operation, such as hard rub or creep, can cause the shaft to bend and become offset from the axis of rotation. Another source of eccentricity that leads to vibration is bearing misalignment. The rotor will shift off center from the axis of rotation, causing vibration. These three examples show that there's more than one way for the center of mass to become unaligned with the center of rotation. This slide will discuss an example of mass eccentricity in a disk. So the picture on the left shows a disk spinning around, and in the upper right-hand quadrant of the disk, there's a small lump. This small lump is causing the center of mass of the disk to be not aligned with the center of rotation of the disk. Now, in this example, the center of mass is offset, likely due to machining tolerances, and the centrifugal force is induced by this unbalance. It is equal to the mass times the eccentric offset times omega squared. The faster the rotor spins, the greater the centrifugal force. In practice, the centrifugal force from unbalance is corrected by an opposing centrifugal force. And this can be done by adding a weight on the opposite side of the mass to offset the vibration. So mass is added or removed to minimize forces due to the center of mass not being aligned with the axis of rotation. These are commonly referred to as balance weights. Typical units for unbalance are inch grams. It can be ounce millimeters. There are many different units that can be used. There are two types of balancing. There's static and dynamic balancing. Power gen components undergo multiplane dynamic balancing. The most simple example of a balancing procedure is the static balance. In this example, the mass axis is displaced parallel to the axis of rotation. All this requires is a single plane balance. This is very applicable to skinny or thin rotating elements, such as an E-class compressor wheel. And on the example for the static balance, the weight is applied at a single plane in the structure. In dynamic balance, the mass axis and axis of rotation are not crossing or not parallel. This requires at least two plane balance correction. And in this, the system needs to be rotating to measure the unbalanced forces. So for a dynamic balance, the mass you're trying to balance needs to be rotating in order to determine how much balance weight correction you would apply. Balance plane positioning. Within a rotor structure, there are predetermined locations where weight is added or removed. Some of these locations are only accessible during the build process, and others are accessible for field balance operations. The axial location of a balance plane is typically positioned to correct for the first and second critical modes. The first mode is a jump rope mode or watermelon mode, where the center of the rotor structure is displacing the most. The second mode, here in the center, has a position or node of zero displacement in the middle of the rotor structure. And the third mode is a more complex mode shape. In this example, a 501D, there are 3 balance planes at the unit rotor level. There is the forward balance plane, located here in the front of the compressor, a mid balance plane in the center of the structure, and an aft balance plane. Individual components can have balance planes for what is called piece part balance. So the individual components can be balanced, and then those can be assembled into a larger rotor structure that is then balanced in additional time. Not all balance planes are accessible in the field. Typically, there are 3 balance planes on longer rotors. There can be even more than 3 balance planes. Here are some examples of mass correction. In the upper left, it is a material on screw type balance. So you can see these multiple holes on the shaft. These gold or brown-like pieces are the balance weights that are actually screwed in to these holes. Here's another example of a screw-in balance weight. You can have material off balance corrections, so it looks like an ice cream scoop removed material between these bolt holes. And then you can have a material on dovetail style. So this green box shows the location of a balance plane on the front of a compressor. And these are the balance weights installed in the balance weight groove. These weights are screwed in and staked in place. There are multiple ways to implement mass correction. There are other ways can actually apply a mass correction by modifying the blades, adding or removing mass. It's not always necessarily on the actual rotor structure. Here's a gas turbine balance plane example. It's common to have a combination of vertical and horizontal balance planes. It just somewhat depends on the shape of the components on which the balance plane is being applied. So this is a forward balance plane on the front of a compressor. You can actually see 2 balance planes. There are 2 mid balance planes, and then there's an aft balance plane. These are all material on dovetail balance planes where weights are actually added into the balance slot. In this picture on the aft balance plane, you can see where the weights are added into this load slot. Here we're going to talk through a typical shop balance process. There's usually 4 steps, 4 main steps, and the process is iterative. Step 1, vibration measurements are taken while the system is rotating. For low speed balance, this is done at approximately 1/10 of operational speeds, or it can be done, a high speed balance can be done, and this is done at operational speeds, and it's done in a bunker. Typically, this is done in a vacuum and done with flexible rotor structures. An example of low speed balance is the upper right picture. This is a 7E GE turbine compressor. High speed balance is a Mitsubishi single flow steam turbine. During the balance procedure, the unbalanced forces are calculated based on vibration data. This is done with accelerometers in the balance machine pedestals. A correction mass is added or removed to align the mass center with the axis of rotation. This is all done by typically with an automated computer-based program. The computer will spit out a weight and angular location for balance planes. The correction has both magnitude and location, so X grams at some circumferential position in the balance slot. After the balance weight is applied, validation runs are completed to confirm the correction worked. This is an iterative process. Here is an example of balance machine screens. These are typical screens showing location and amount of unbalanced reading. These values would be compared to the spec requirements, whether it's an ISO spec or an OEM specific spec. In the picture on the right, you can see the amount of mass to apply and the circumferential location to apply this mass, 5 grams at 60 degrees. And in this screen, you can see that there's more than one balance plane 1 and balance plane 2. In both cases, the required weight is similar, 5 grams on plane 1, 7 grams on plane 2, but the angular location is different. In this case, the screen provides the unbalance in terms of inch grams and circumferential location. Determining the allowable unbalance, there are many specs. There is a American Petroleum Institute spec, ISO specs, mil specs. Within the ISO spec, there are various levels of allowable vibration, balance grades, 1, 2.5. They can go up higher. But for a comparison, we will take a rotor that weighs 1,000 pounds, that's rotating 3,600 RPM. And here are the various levels of allowable residual unbalance. The API is 14 inch grams. ISO with a balance grade of 1.0 is 26 inch grams. The mil spec 167 is 34 inch grams, and ISO balance grade 2.5 is 54 inch grams. In all cases, the allowable unbalance is a function of rotor weight and speed. The specs, whether or not they are industry or OEM, detail the amount of allowable remaining unbalance. And the goal is to minimize this to a specific requirement. It's never zero, but it's a very small number. And we will go through an example with the ISO spec to understand how small the allowable unbalance can be. This is an example using the ISO 1940 spec. So we're going to use a balance grade of 1. The weight of the rotor is 35,000 pounds. The full speed is 3,600 RPM. We will assume the balance plane is located at 18 inches radially from the center line of the rotor, and that we are implementing a 2-plane balance. Using the ISO spec, for the service speed of 3,600 RPM for a balance grade of 1, so we find 3,600 on the x-axis. We come up to the balance grade of G1, then come over to read the allowable eccentricity. The total allowable unbalance is the rotor weight times the allowable eccentricity. So in this case, it is 0.4009 inches times 35,000 pounds. The total allowable unbalance is 1,429 inch grams. Once again, this is the rotor weight times the eccentricity. The allowable eccentricity is a function of the speed and the balance grade. If we had chose a different balance grade, such as balance grade 16, there would be an increase in eccentricity, which means an associated larger amount of vibration is allowed. In the ISO spec, the smaller the balance grade, the smaller the allowable residual unbalance. So in this case, if you have 1,429 inch grams allowed, if you distribute that on 2 balance planes, each balance plane is allowed 714 inch grams. At 18 inches, the radial location of the balance plane, this means that you need to add a weight of 40 grams to correct any sort of balance. Nickels are about 5 grams, so this is the equivalent of 5 nickels. The result of this calculation shows that the typical residual unbalance requirements for power gen hardware is very, very stringent. Once a unit is built and shipped to the field, vibrations are still measured, and the unit vibrations are a key measure of unit health. Unit tripped on vibes can be the first clue of a larger issue. Seismic and proximity probes are used to measure vibration. Proximity probes are a direct measurement of the rotating structure via an eddy current style probe. Seismic is a vibe sensor mounted to the casing. Vibrational characteristics of rotors in the field can change over time. A crack can develop in the rotor structure. Rotor or rotor bolts could creep. A new rotor could have been installed in the unit, which has different characteristics. New blades could have been installed, causing vibrational issues. A sensor could fail. A balance weight can fall off, or consistent with the picture on the right, balance weights can actually lose mass and not be effective in correcting any known vibration issues. This first case study is a double flow LP gland machining. 2.4 inches were machined off the diameter due to a hard rub. In this picture, you can see the location of the hard rub spots. They are not, the rub was not equivalent depth all the way around. This hard rub induces high temperatures into the rotor structure, which can cause a rotor bow. As material is removed, to remove the damaged material, the rotor can bow even more. So in this case, hot spotting was done to reduce the indicator run out or movement to a reasonable level, and then a new center line was machined by removing material off the outer diameter of the rotor structure. Hot spotting is both science and art, and this can be used to correct out a bowed rotor structure. After all the processing, heat treating is done to the material to ensure the rotor properties meet design intent. In this case study, a mid-plane balance location was added to a rotor structure that did not have a mid-plane. This rotor had 2 balance plane locations and needed a mid-plane to ensure the vibrational characteristics of the rotor were kept sufficiently low. In this case, a proposed location was found on which a vertical balance plane could be added. In this case, a simple FEA assessment was completed to determine that that location was appropriate for a balance plane to be added. Our FEA assessment determined there was sufficient life capability in this location, and the balance plane was added. This is the end of the webinar series. If there are any questions, I'll be willing to ask them. Please note that registration is open for our September 23 training course in Las Vegas, Nevada. This will be co-located with 2 Kestrel courses. So Kestrel and TGA will be providing training in September 2023. All right. If there are no more questions, that will conclude this webinar. Thank you for your time.